Hi, I want to take you through an example of finding the slope at a point and finding a tangent line to a curve. The example is going to cover most of the important topics that are in Chapter 3, including limits, the limit definition of a derivative. So here's our example. Here's what we want to do. For some general function f of x, we'd like to find the equation of its tangent line at some point x equals a. Turns out that we can find the derivative function. By taking the derivative and finding a function, we can then plug in later. So we're going to have two different approaches here. We're going to first find the function f prime of x, and then we're going to plug in x equals 1. The second approach we're going to show is finding f prime of 1 directly using limits. These are both valuable approaches, so I'm going to show all the algebra for both. Here's a picture of the situation. We have a secant line, right? And if you think about it, these points are f of a on the left and f of x on the right. So we just look at the slope formula, right? This is just a slope formula, the change in the y values divided by the change in the x values, and we take that limit as x approaches a. Right, so let me switch back. I have it here both ways, but I'm going to show you with the a and x version first. So here's the secant line through the point a comma f of a and x comma f of x, right? So again, this is just the slope, the divided differences, the change in the y values, f of x minus f of a, divided by the quantity x minus a. Okay? So that's what we're doing, taking the limit as x approaches a. The other formulation, we just make a switch, and instead of thinking of this as the point f of a, we're going to think of it as x. And instead of thinking this, we're just going to consider the distance along the x-axis between these two as h. So that requires the simplification the substitution right here. So let's show that situation back on our dynamic graphing, right? So these 2 points, instead of a and x, I can have these 2 points be x and x plus h. Sorry. There we go. Sorry, took me a second. And there should be one more here. There we go. So this is the same situation as before, except instead of having a here, we have x. Instead of having x here, we have x plus h. And now the function values are the same. We just have, in the numerator, we have f of x plus h minus f of x. And when we take x plus h minus x, we just get the h in the denominator. So as we take this limit as h goes to 0, the limit will give us the slope of this tangent line. Sorry for the glitch there on the graphics. I'm just learning this new technology, so hopefully it will get smoother with time. So we're going to start with this formulation, the limit as h goes to 0 formulation. And the first thing we're going to do is we're going to substitute. So the function rule is x cubed minus 3x squared. So the first term in brackets here is just x plus h substituted in for x in the rule of the function. And then of course the second brackets here is just the rule itself, because that is f of x. All right, and what we're going to do is we're going to expand in the numerator using Pascal's triangle. The third row of Pascal's triangle is 1, 3, 3, 1. So we have the pattern of the powers there. X cubed is the first term, then x squared h is the second. Xh squared is the third term, and the fourth term has h cubed, and we get the coefficients from the third row of Pascal's triangle. We can also use Pascal's triangle here. The second row of Pascal's triangle is 1, 2, 1. The key thing here is that the red and the blue terms are going to add up to 0, so they'll go away. So when we distribute everything in the numerator, we can get rid of the parentheses, and you'll see that for the red x cubed, I have a blue negative x cubed. For the negative 3x squared, I have a positive blue 3x squared. So those go to 0. The only things that are left are in black. And notice that every black term up here in the first equation has an h in it. All right, so that means that every single term in my numerator in the second equation here has an h in it, which can be factored out. So the h's cancel, and we can evaluate this limit by direct substitution. Since I'm no longer dividing by 0, I can just plug in h equals 0. Well, notice that any term that has an h in it is just a 0 term. There are only two terms that don't have an h in it, the 3x squared and the negative 6x. So those are the only things that are left. So 3x squared minus 6x is the rule for the derivative function. This is the derivative of f of x. And this allows me, if I can find the slope anywhere on the real line. I just plug in the x value where I want to know what the slope is, and this rule, 3x squared minus 6x, will give me the slope of the original function at that exact location. Okay, that concludes the first approach. The second approach was to use limits directly to find the slope at a equals 1. So we're going to take the limit as x approaches 1, right, because a equals 1, of f of x minus f of 1 over x minus 1. Again, we're going to substitute using the function rule, all right, and we're going to do the same thing as before. We're going to put the cubed 1 with x cubed and this squared 1 here with the 3x squared, and notice that there is a 3 out front in both of those, so it can be factored out. So you see the 3 got factored out here in the third equation. But you should be able to get between the second and the third with relative ease. And now we have a difference of perfect cubes and a difference of perfect squares. Those patterns, if you don't know them, you can Google them real quick. But that's just expanding using those factoring patterns. And notice that I have an x minus 1 term in both of an x minus 1 in both terms on the top that can be factored out. So here's what I had. This is the same as the last equation on the previous slide. Here's the x minus 1 being removed. I apologize. That says x minus a, but a equals 1. So sorry, we're trying to factor out an x minus 1 from both terms. We're going to cancel it, so we're just left with the part in the brackets. And this is great since we're no longer dividing by 0 when we directly substitute, right? So if we look at this direct substitution, we would be substituting in and getting a division by 0 problem. But when we cancel the factors x minus 1, top and bottom, we're just left with the part in brackets, and then we can just plug in 1s, right? So I have 1 squared plus 1 plus 1. which is 3 from the first group, and from the second group I just have 3 times 1 plus 1, that's 3 times 2, which is 6, so I have 3 minus 6, which is negative 3. So that's the second example completed. Let's compare it to the first example. We said when we take the derivative as a function, we can plug in any x value we want and find out what the slope is at that x value, at that point, x comma f of x. Well, let's do it. We were evaluating this where x equals 1. So plug in 1 here. You have 3 times 1 minus 6 times 1. That's 3 minus 6, which is negative 3. So those are the two approaches, calculating the derivative as a function and then plugging in, or we can take the limit as x approaches the x value we're interested in this case, as x approaches 1. So now we have to write the tangent line. We know what the slope is, so we can use the point slope formula of a line. Now the point slope formula of the line is just the slope of a line, and if you think about it, right, the slope of this line would be y minus y naught divided by x minus x naught. Well, we've just multiplied through the slope equation by x minus x naught. And so if you ever have trouble remembering the point slope form of a line, that's the way we get it. We get it directly from the slope formula. And now we're going to plug in. Right? We first of all need to know what point we're talking about. So we need to evaluate f of 1. But that's 1 cubed minus 3 times 1 squared, which is negative 2. 1 minus 3, which equals negative 2. So that's this value here. That's how we know the point that the tangent line has to go through. A point that the tangent line has to go through. So we're going to plug that in using a slope of negative 3. So using the formula, I have y minus a negative 2. That's the y value from the point we know. Negative 3 is the slope, and then I have x minus positive 1. Well, positive 1 was where we were trying to find the tangent line, the x value where we're trying to find the tangent line. And that simplifies to y equals negative 3x plus 1. Again, understanding this is the heart of chapter 3. So hopefully this video, this new approach to teaching actually makes sense to you. Have a good morning.